local and geometrically local Hamiltonian or says is plane model. Okay, but in plane model we have HR assumption. Okay. So then we have So then finally we go to the proof ideas, and the proof idea use some well-known result between Hamiltonian evolution and quantum algorithm. So basically, there are well-known results that you can transform back and forth between Hamiltonian evolution and the quantum algorithm for solving problem pretty nicely. That's also why you can embed parity into Hamiltonian simulation problem. So the idea kind of looks like this. So you have some problem f of t of x. Okay, so this is some problem that depends on your evolution time t. And because we can do this transformation back and forth, so then this is a quantum algorithm problem. And so we embed this into a Hamiltonian simulation, means that there is some Hamiltonian simulation that if you run it successfully, then you can calculate this function here, ft of x, because it basically do some quantum algorithm. Okay, and then we say then if we have a quantum computer that do simulation of our Hamiltonian evolution really fast, so you simulate in depth less than t. And then we string these two t together. That means we have an algorithm that calculates this f to a t in really low depths. Okay, but then we go back to see that our f of t we have constructed to be a very hard function. Means that this is a function that need omega t depths. Okay, and so this thing contradicts with this thing, and that means we have some contradiction here. And that means something doesn't work, and the only thing that doesn't work is this thing here. It means that we cannot have the simulation in depth less than t. Okay, so this thing doesn't work. Okay, that's kind of a proof sketch. So yeah, so we need to find those functions that's parallelly hard. That even if you query in parallel, it's really hard. Okay, and we are really short in time, so let's go really fast the rest of the proof. Okay. And so as we say, we have 3 results, and here is a high-level summary of the result. And we actually have 2 different f of t. Okay, so the first f of t, this is how we do the sparse Hamiltonian in Oracle model. It's just a permutation chain. So you have a whole bunch of random permutation and chain them together, and you want to calculate this chain. So this is a chain with t different permutation. And as you can imagine, so if you query, if you don't query the permutation in sequence, then you query the later part of the permutation. You don't know which position to query, and that's useless. And you really need to query those permutation in sequence. And in the local and plane model, we use 2 things. So first, we change our quotient. So we use twisted hash chain, which we'll have a picture later. And yeah, and we make it in plane model because we just use this SHA function. So it's a secure hash algorithms to simulate a hash function. So this is some hash function that in cryptography we believe that's secure. Okay. And in the last minute, let's try to go this really quickly. So first is the idea about query depth. So query depth means that we have those queries in our algorithm, and so we can have parallel queries, and they are kind of free. And in our counting, we only count the depth of our query. So we have parallel queries in each layers, and we count how many layers do we need to use these. Do we need to place those oracle in our circuit? So here we have depth 3 here. Okay. And we have those random permutation, and we are asking that starting from the O0 state, we apply those random permutation, and where do we end up with? And we show that to actually calculate this, you need to query the 1, 2, 3, 4 in sequence. Okay, and then there is a twisted hash chain, means that so basically we have 2 registers that are both n qubit, and we just to have those hash functions that's just a random function. So it's a random, maybe every string to a random, every NB string to a random NB string. And we add this x0 and the random hash to here, and add it back, and apply another hash, add it back, etc. And we do these t times. And yeah. And one thing about why we need to do this twisted, so if you think about chain of h function, you kind of think you can just keep applying a h function on input, and but you will look at this, and so the number of qubits will scale, and we will get worse parameter. Okay, and yeah, and just one thing about how we prove the twisted h chain is hard, is that we use this compressed oracle technique developed by Mark Zandri. Okay. And yeah, and as we said, so this is also in oracle model, but for random function, we have this random oracle heuristic, basically believe that those SHA functions can simulate a random oracle really nicely, and they are secure. And because we just replace those random oracles with SHA, and we believe that in plain model, calculating this is also hard. So we require some yeah, so we require some OD time. Okay, and yeah, so I think I'm going over a little bit over time, and so this is some outlook. We want to get better parameters, and thank you for bearing with me, and I'm happy to hear any questions.
Okay, thank you.
Yeah.
Okay, time for questions.
Okay.
To look at this problem, hoping that, or trying to prove or disprove that cannot have a faster algorithm in this context. Was there some intuition that suggests that you can actually do it sublinear or faster, or was it just that it will be good to show that it's impossible?
I could show it's impossible, so this is a rigorous proof. So because it is an oracle lower bound, right?
Yeah, I mean, in the end, you show that it's impossible. But I mean, what was it that led you to think about this question to start with? Was there anything that suggests that maybe it was possible or it could be possible?
You mean, was there a suggestion is possible, or
was there any hint or any results in the literature or any intuition that led you to think that maybe it could be possible?
It couldn't be possible. Okay. So yeah. So why is this? The intuition is kind of, I guess, here. So here is the picture in my head about a chain of random permutation. Okay. So we have this we have those NB string as H line. Okay. So we have those dots, and we think it as NB string. So it's from 0 to n to 2 to n minus 1. Okay. And the random permutation basically made you randomly permute those NB string, right? Okay, so you made this 0 to n to some string, and then this 0, 1 to another string. Okay, and so we have those random permutation that map each layer of those string to, so you have different connections. Okay, and yeah, and the question is, if you do these t times, so you compose those t layers, and where does the 0 to n get mapped into? So you see the 0 to n will get to random location, and they will end up somewhere here. Okay, and the idea is, everything in algorithm is like a scale polynomial in n, and here we have 2 to the n. Okay, so you cannot look up everything. Okay, and how do I say? Okay, and the idea is, if you don't do this in sequence, okay. So the naive way to solve this is you just query this in sequence. So you query first permutation, and you know this location, and you query second permutation, you know this location, etc. And you can walk along a line to the end. But if you want to jump ahead to parallel phase forwarding, then maybe you need to look at the first location and like the third location. You need to find this line and this line together, right? But the idea is that you cannot find this line really fast, because there are exponential number of lines here, and you don't know which line to look into. Okay. And yeah, so that's kind of idea. You hide this because the permutation is over 2 to the n b string, and so if you want to do phase forwarding, you want to look ahead really fast, you don't really know where to look into. So you must go through this one by one, and so you need to do this in sequential.